Welcome to the Math Record. Today we'll learn about logarithmic functions. This video would cover part 4 of chapter 3 in our Precalculus class. In this video, we will introduce the idea of logarithms and their properties and solve logarithmic problems. Okay, let's begin. What is a logarithm? So, a logarithmic function. What is a logarithmic function? Basically, in our previous video in part 3 of chapter 3, we explained the idea of a exponential function, which looks something like this. Now imagine a function that is inverse of this. When we talked about in part 2 of chapter 3, an inverse function is a function that's like a mirror of y is equal to x. So it's like kind of flipped over this mirror. It's going to look something like this. These logarithmic functions are important because they are used commonly in multiple applications, but also in math, it helps us solve exponential questions. These are used in the logarithmetics and exponentials interchange, so then you'll be able to solve like difficult questions. So this is what it looks like. This will be a logarithmic function. It will be so what will be defined would be technically an inverse of a exponential, which be fine enough to learn in this course. We won't be covering too much about logarithmics, but there would be applications that we're gonna discuss about it. So first up, how do we write a logarithmic function? So basically, a logarithmic function would be written as y is equal to log, because it's called logarithmetic, and you gotta write something in the base. It's saying something that's written to exponent. Now it's gonna be on the bottom, so it's gonna be on the base. So we're gonna have log a of a variable x. So that's basically how you write a logarithmic function. So this would be the same. The reason they write this is that this form is the same thing as saying y to the power a to the power of y is equal to x. So let's do like some kind of practice with this. So let's say we have y is equal. I'll write out the property here first. A to the power of y is equal to x. So let's say you have y is equal to log 5 of x, right? And you want to find out when y is equal to like 1, right? I mean, when y is equal to 1, right? So you have 5 to the power of 1 is equal to x, because you just substitute it in, because you want y is equal to 1, so you put y as 1. A is 5, because right here, and it has x. So log 5 of 5 is equal to 1. So these will help us solve for the exponents now. So this is what you do. So when I was talking about the solving exponential questions, and what we were solving for is the exponents in our in the questions that we're trying to solve, but I wasn't able to explain in this video. And this is how you're gonna do it. You're gonna use logarithmic functions. You're gonna look for the exponents now, because that's what this equation calculates for, the exponents. So, but there would be getting into decimals. You would have to be able. You're gonna have to be using a calculator like 20 billion times in logarithmetics. Like your calculator would be like your best friend. So that's what a logarithmic function of base a is referred to as. And let's discuss like the properties of that function. So like similar to how we did with exponentials, we're gonna talk about domain and range. Remember, this function, a logarithmic, is an inverse of a exponential. So if this is an inverse, the exponential domain, I'm not gonna write the entire thing. Domain is negative infinity to infinity, right? And the range is 0 to infinity. So remember what I said in chapter part 2 of chapter 2, where I said the inverse of any function where its domain becomes its range and its range becomes its domain, well, it's going to be applied to the same thing as exponential to logarithmetics. So now if the logarithmetic is the inverse of exponentials, right? So the domain of the exponential is the range of the logarithmetic. So it's going to be negative infinity to infinity. and the range of the exponential will become its domain. So it becomes 0 to infinity, which makes sense because you have something that looks like this. The exponential will look something like this, right? And you have something like a mirror, and you have a graph that looks like this. So if this line can't cross this axis, that means mirroring. This means this line can't cross this axis. So it goes from 0 to infinity, right? And then you have the range, which is negative infinity. As this goes to negative infinity, this also goes to negative infinity. This goes to like a really big number. This also goes to a really big number, which also to infinity. But it goes at a slower rate, right? So basically, you see how this how this works, which makes sense. So that's how like logarithmetics, like the property of logarithmetics. Let me erase this. Let me write this back again. So 0 to infinity and negative infinity to infinity. Like similar to exponentials, we're gonna talk about its x and y intercepts. Unless the graph is moved over, like imagine that was the original graph and the new graph is like this. Oh wait, sorry, that's not a really good picture. Like this. Then it's gonna have a y-intercept, but regularly when it looks like this, since it never crosses the y-axis, since like the exponential never crosses the x-axis and you kind of reflect it over, it's never gonna cross the y-axis, so it's never gonna have a y-intercept. So a logarithmic function has no y-intercept. Now we're gonna talk about its x-intercept. It usually only has one, so right here. So you could just calculate it if you have it. So you have something like y is equal to log 5 of x, and you want to find when y is equal to 0. Just put 0 is equal to log 5 of x. Log 5 of x. And 5 to the power of 0, remember the thing that I said in the beginning of the video, equals to x. Right? So, anything that's raised to this power, remember the exponential rule is 1. Anything raised to the power of 0 is 1, so x is equal to 1. So usually the x-intercept is 1. Unless this number is like really strange. Like instead of saying it's log 5 of x, it will be log 5 of like 2x. Then you have something like 1 is equal to like 2x, and x is equal to 1/2, or something like that. But usually it's going to be 1. The x-intercept is going to be 1. So the 0 is usually 1, basically. And now asymptotes. Remember how an exponential has only a horizontal asymptote at y is equal to 0? So if you made a mirror and you kind of made an inverse that looks like this. Sorry, it's a bad picture. The only asymptote, which is right here, is now reflected across to the y-axis. So the only asymptote is this line, the y-axis, and the y-axis is just x equals 0. So now our since a exponential has a horizontal asymptote, and now it's flipped over a mirror to get this the mirror y equals to x to get the y-axis. X over 0, x is equal to 0 is a vertical asymptote. So you have a vertical asymptote, which I'll write as VA, is equal to x is equal to 0. So that's where our vertical asymptote is going to be. That's basically the general process of the general properties of a logarithmetic. You really don't need to remember all of it, but it's good to know. And now we're going to actually talk about some logarithmic properties. Like, not the graph properties, but the actual properties. Like how exponentials have properties like 2 to the power of x times 2 to the power of y is equal to 2 to the power of x plus y. Logs have similar properties. Let's discuss the first property. Rule 1, if we have log b, sorry, that doesn't look like a b, b of, like, in the parentheses is m times n. This is the same thing as saying log b of m plus log b of n. This is the same thing. Now, if this is plus, right, what happens if this is log b of m divided by n? This would be log b of m minus log, sorry, minus log b of n. Remember to keep track. So m right here and n. And now we have something like a power rule. In this case, would be log b of mk. M to the power of k. This would be the same thing as k times the logarithmic, which is log b of m. So you can move a k to the outside. This property uses the same concept as like a to the power 0 is equal to 1, like just anything. Instead of 0 to the power 0, as I explained in the video before, we have log b of 1 is equal to 0, right? Because b to 0 is equal to 1. Because if you just use that main property, which is just log a of b of x, is basically a to the power of x is equal to b. So this property is the same. This is equivalent. This is equivalent to this. Always is always equivalent. So that's another property of that one. So also, if we have something like log b of b is also equal to 1. Because if you think about it, it's b to raise to the power of 1 is just b. So this property is always true. But it's a basic property that you probably could just test later. And you have log b, b raised to the power of k, it's going to be k. Because think about it, if you just put k here and this is b to b, which is 1, then it's just k. Or now if you have b, which is exponential, to log b of k, this would just equal to k, okay? Which is also a pretty interesting property. Because imagine, they're inverses, right? Because a inverse function, if you put the domain into its range, but they inverse, because like the domain of a function and its inverse would be its range. So it's, and vice versa, right? So basically, what it's saying is that if you put 1 and it gets 2, then the inverse is domain is 2 and 1, then it's gonna get 1 to 2 and then back to 1, basically. So what it's doing is that you put a b to the k, you put a k which goes to this function to a b, but to get a new value, but that new value returns it because this function, because this is the inverse of the exponential, then it gets that original answer back, so it just gets k. So this is what it's doing. You kind of just want to memorize it, but it's good to understand what it's doing. So that's an interesting number, and overall, all these properties like work if like if b is greater than 1, you know? Like it could be like any real number basically. But those are some rules like you want to just know, you know. So those are the log rules that you want to memorize. You might only want to memorize just log b of m times n is equal to log b of m plus log, sorry, zoomed in too much. Sorry about that. And log b of n. And you have log b of m divided by n is equal to log b of m minus log b of n. And you have log b of m to the power of k is equal to k times log b of m. These would be the main ones that you want to know. There's also one more that that usually like the school wants or like the course wants you to know. It's basically this is gonna be used like the most often if it's like really difficult. Like it's gonna use something like if you have something like log b of a, it's gonna be written as log a over log b. And this could be any base. Like this could be any base. So if we have log a, 2 of like 5, it's gonna be written. It could be written as log 10 of 5 over log 10 of like sorry, let me write the just the logs. Log 5 over log 2. You can put this at 9. You can put this as 8. Put this at 7. It doesn't matter. It just has to be this. It just has to be log 5 over log 2. So that's what it has to have. And it's called a change of base. That's what the property is usually referred to as. Because it helps you, because usually what we use is we use a base 10 system because we count from 0 to 9, right? So that's 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are 10 numbers. So we use a base 10 system, basically. So B would be 10. So if we have something like if they just write something called log 9, it's gonna just be basically log 10 of 9. But since this is a common base, they usually don't write it. So that's basically what they write. So if you put like log 2 of 9, basically you could just write using the change of base, you could just put log 9 over log 2. And if you plug that in your calculator, you get it right. Because if you don't know how to put in log 2 of 9, then you just also do this. So yeah, it's an interesting property that you're gonna use a lot. Also, they might introduce something called a natural log, uh, like how exponentials like have something called a e. Logarithmetics, like from the interest one that I talked about, like when you're calculating money, log has the same concept called ln, which is called natural log. Natural log is basically just the inverse of e. That's basically what it is. Like imagine a logarithmetic. Uh, imagine So we have something like 2 to the power of x. The log version would be log 2 of x. So let's say you have something. So if you have an exponential that's e to the power of x, right? It's gonna be referred to as ln of x. That's what it's gonna be written as. You know. So it's just a special case. But it's basically just like a special number because e is equal to 2.718, like etc. Because I don't remember the rest of the digits. Then log just does the same thing. It's just like log e is basically just ln. That's basically what it means. So that's natural log. It's not anything special, but if you want to do compound continuous and you want to solve those questions, you're gonna have to use ln. But it's just a special case of just saying log e of like a, which is just ln of a, basically the same thing. Ln has the same properties of log, so like the same graphs and the same like rules as logs, because it's just, although it's a special case, it still follows the same format, you know. So now let's like solve those like exponential like questions. So you have something like, I don't remember the questions, but let's make up an example. So let's say like 300 times like 1.1 to the power of 5x is equal to like 600, right? Like when would this number double? Now we could solve something like this. So you have 1.1 to the power of 5x is equal to 1/2. And now we could remember how like we have log of b of a is equal to y, and now you could change it to y to y, b to the power of y is equal to a. Basically, that's what we're gonna do here. So now we're gonna have log 1.1 to the power of 1/2 is equal to 5x. So that the rules make sense. So you just put the base, it's the base, and you put the answer next to it is equal to the exponent. And you could use your calculator for this. This is why I said your calculator is gonna be like your best friend. So you're gonna put log of 1.1, log of 1.1 to the power of, I mean not power, log of 1.1 of 1/2. You get some kind of like negative number. You get something like negative 7.2. Sorry, did I write that wrong? 1.1 to the power of x. Oh, sorry, I'm writing this wrong. So this is 2 because 600 divided by 300 is 2. Sorry, I messed up about that. So you put log 2 of 1.1 is equal to 5x, and you plug that into your calculator. And you have log 2 of 1.1, you get something around like 0.1. Using your calculator, you get 0.13 like 75. I usually write fours like digits in the decimal place is equal to 5x. And then you just divide by 5, and you get x is equal to like 0.02 like 75. So that's like the answer, and that's how you solve it using log. But you're gonna be using your calculator for this. I mean, not this one right here, because you're not gonna be able to know the answer by just doing regular math. There is a method, but we're not gonna be teaching it in this channel, which is just like a bunch of tables to memorize, which is not fun. So what you do is just use your calculator, which a majority of like mathematicians do. So now you're gonna have something. So that's basically how you do like what logs like. That's basically the general case for like all logs now. So if you want to like do the special case for like the exponent, which is like, let's say like 2 to the x minus 4x, 4 times 2 to the x plus 3, and you want to solve for the zeros, you have like 2 to the power of x minus 1 times 2 to the x minus 3 equals 0. So 2 to x is equal to 1, and 2 to x is equal to 3. So you say log 2 of 1 is equal to x, and log 2 of 3 is equal to x. So you use your calculator. Log 2 of 1 if equal to x, x is just 0. And this x is equal to log 2 of x, which is, now you could do it, which is 1.58 like 5-ish approximately. It's gonna come out to like a really weird decimal, so you're just gonna have to write like a few of the digits. You don't have to write all of it, because they don't expect you to find the exact answer. They're gonna have you get like an approximate answer. Anytime you're rounding, you're gonna get an approximate answer. It's not the real answer. So it's gonna be, so that's how you solve something like that. Like a special property that you want to know, like this is just for the end, just for fun. But like it's an interesting property, but it says how can you switch from log to ln? How does that work? So what you do is that basically you're gonna use the change of base property. You're gonna have log, let's say b of a is equal to log a over log b, right? And they're both base x. Imagine if the x was equal to e. So now you have log b of a is equal to log e, which is just ln of a over ln of b. You see how that works? Now you can switch it to ln, which is the same thing. So ln of log b of a is the same thing as ln a over ln b. And if you want to switch like equation from like log to like like, and this is what they would do, so you could switch from a equation like from y is equal to like 2x to like an equation of y. If you want to make it continuous, right, you got like e to the, like what e to the power of would be the same thing as 2 to the power of x. What will be the same thing? So that's what they will be looking at, and that's the same thing as saying like ln of 2x. Because think about it, because remember the property that says like um that says that b the power of log b of k is equal to k. Well, this is the same concept. So b would be e, right? And log e would be ln, and k is equal to k. But you have x here, right? So that's basically how you would like basically do it. So that would be like ln of 2, and then you have like this all to the power of x. So that's just k. So this would just, so what this would get us is like, it's just, what you write is like, this is in the parentheses, like this is all the entire exponent. So I mean ln of 2, it's not ln of 2x, it's ln of 2, it's e times ln of 2 times x, but they're both in the exponent. It's not ln of 2x. Because you want to specify where you're going to put the parentheses. So you put ln of 2x. Because if you want to have the x be ln'd, it's going to be like ln parentheses 2x. You see how there's difference? So it matters where you put those brackets, basically. So basically this part would be saying it's ln of 2 times x, which is the same thing. Because this part right here would just simplify to 2 because of our property that I showed before, which is still raised to the power of x. So that's how you switch from like base 2 to base e. And that's why logarithmics are important, because this helps us rearrange into a different equation, which is kind of similar, but in a different way. We could like visualize it a little differently. Anyways, thanks for watching, and I'll see you at the next math record.